In using statistics in real life, it turns out that we take statistics from samples and we make estimates of parameters of populations, and we sprinkle that a little bit with reliability information, with error factors and such. Okay, that's what we do in real life. But to learn about the situation, the relationship between the accuracy of statistics and parameters, we need to rather unrealistically start with ideas that we know aspects of populations. That is, we know parameters, we know the statistics, and we relate those mathematically, and then we sort of extrapolate those relationships to samples generally. All right. We're going to begin the process now with a rather unrealistic population, and this is a population of the heights of basketball players. And these are all in inches, 76 inches, 78, 79, 81, and 86. Okay, so this is a population involving heights of players. And mu, the mean of that population, is 80. Okay, add them up, divide by 5, we get 80. All right, now, let's take samples from this population. I want to take all of the samples of size 3 from this population. And I'm going to assume, which is rather unrealistic, but I'm going to assume that we have no replacement. That is, if I randomly take a height measure, I don't put it back in order to select another one. That is, when I'm selecting 3 items from randomly from this group of items, I can't get 76, 76, 76. Okay? All right. Good. Now, all of the different groups of 3 from this group of 5 would be 76, 78, 79, 76, 78, 81, 76, 78, 86, and so on. There are 10 of them. All right, so these are all the samples where sample size is 3. Now, from each of these samples, I have calculated an x bar, that is the mean of the sample. So the mean in this sample, add these and divide by 3, and I get 77.7. From this other sample, I add these, divide by 3, I get 78.3, and so on all the way down. Now take a look at these. They're different from one another, except for these two. These two happen to be both 81, and the others are different. And so we have 9 different ones. 2 of them are the same, but let's just say we have all 10 of them different. Now, if they're all different, then the value of x bar is random. So x bar then, in this distribution of sample means, the sample mean is random because the sample mean depends upon the sample that is chosen. And if the sample that's chosen is a random sample, then the x bar is a random variable. Okay, they have, therefore, a probability associated with them. We can associate a probability with the idea that this will be the x bar that is chosen, or this will be the x bar that is chosen, the sample mean, you see. Now, if that's true, then each of these has a probability, that there are 10 of them, each of them has a probability of 1/10. They are equally, the samples are equally likely to be chosen, so each of these is equally likely to be calculated. Right? And I'm saying equally likely, I'm showing that 81 appears twice here, so that doesn't change the situation. All right, if that's true, and each one of them has a probability of 0.1, since there are 10, the probability that any one of them is chosen is 0.1, then we can figure the probability, we can calculate the probability that the mean of a sample will be within 1 inch of the population mean. That is, we want to calculate the probability that our x bar value is within 1 inch of 80. Now remember that the population mean was 80. So it means then that the x bar will be between 79 and 81. Whoops. Okay. Now we can make that calculation just by observation. How many of these values are between 79 and 81? Well, let's see. We have 77.7 outside of that range of values, 78.3 outside of that range, 80, yeah, that's in that range, 78.7 outside of the range, 80.3, check, 81, check, 79.3, check, 81, check, 81.7 outside, 82 outside. Okay, we have 1, 2, 3, 4, 5 out of the 10. 5 out of the 10 that are in this range. So the probability that a mean of a sample in this distribution will be within 1 inch of the population mean is 5/10. All right. Now, what do you think would happen if I took samples of size 4? All of the samples of size 4. It turns out there aren't as many of those. There are only 5 of them. Would those sample means be closer to the population mean or not? Well, we can see it from this chart. Now, I have the values in the X distribution, in our population that we started with. I have them on this graph. All right, the one height was 76, another was 78, another was 79, 81, and 86. Those were the heights that we started with. The mean mu at 80. Okay, that's the X distribution. Now, the X bar distribution for n equal 3 is here. All right, and notice how the spread of values as expected would not be as spread out as the X distribution. So this is the X bar distribution for sample size 3. Now, then I took sample size 4 and I performed the same kind of calculation. That is, I took each of those samples of size 4 and calculated an X bar, or a mean of each of those samples. And I have graphed those here, and just with a little open circle. Now notice how when the sample size got a little bit bigger, that the spread of the X bar values narrowed. That's a very important idea in our study. It's a rather general idea. We want to be a little more specific with how much that spread is narrowing, and we want to make a calculation for it, but we want to see it visually here first. So these are the X bar distributions, the solid dots for n equals 3, sample size 3, the open dot n equals 4. All right, and here's the comparison to the X distribution. Now, if we have less spread of the information here, what do you think about the probability then for this distribution, for this X bar distribution, that the heights or the values will be within 1 inch of the population mean? Well, let's go calculate it over here. You see, here was the calculation that the probability that a mean of a sample of size 3 is within 1 inch of the population mean. And I'm going to make a note here that this is for sample size 3, and here we're going to calculate the same thing for sample size 4. So we're calculating exactly the same thing. All right, let's go over here and calculate. We're looking for values of the X bar in this sample size 4 distribution, values that are between 79 and 81 inclusive. And over here, let's see. Here's 79, and let's see, I'll just extend this down a little bit. So all of these values, and including this one, it turns out that this is exactly 81, this last one over here. So all 4 of these out of the 5 are within that range. And if 4 out of 5, gee, that's 8 out of 10, so the probability is this. Now we can think of it another way. We can think of, okay, each one of these has an equal probability, so the probability of each one is 0.2. So that's 0.2, that's 0.2, that's 0.2, that's 0.2. The ones that are within the range are all of these, 0.2 and 0.2 and 0.2 and 0.2, that's 0.8. Okay, so we have sort of an 80% probability that these X bar values are within 1 inch of the mean of the population. Now notice that the point of this is that within a given range of values, we are tighter within that range if the sample size is larger. And that's the point I'm trying to drive home here. There's another point that I want you to see, that if you calculated the mean of this distribution, the mean of the x-bar distribution where the sample size is 3, you would find that the mean of that distribution is exactly 80. And if you take the mean of this distribution where the sample size is 4, the mean in that distribution is exactly 80. That means that, just extending this down here, that this, the mean of the population is the same thing as, is equal to, the mean of these x-bar distributions, you see. Okay, so they would be 80 as well. Now, it's time that we talk about standard deviation, because standard deviation is the measure of the spread of values, the spread of the information. And so what we're seeing here is that the spread involved in the x distribution is one thing, something to be calculated, and that spread of values in our x-bar distribution of sample size 3 has narrowed, and the spread when the sample size is 4 has narrowed yet again. Let's calculate that narrowed spread of information by calculating standard deviations of all of these. Okay, standard deviation for the population is sigma. We can calculate it using this formula, or there are other ways to do that, but at any rate, making the calculation, we find that the standard deviation for the population is 3.41 inches. If we make a similar calculation for the x-bar distribution, when sample size is 3, we find it to be 1.39. And when sample size is 4, we find it to be 0.85. So we're noticing a reduction in the standard deviation of all 3 of these groups that we're talking about. Now, one idea is the notion that an x-bar distribution, a distribution of sample means, is by a prescriptive amount, by an amount that we're going to calculate in just a minute, smaller than the standard deviation of the population. And the other important idea is that as the sample size increases, that standard deviation decreases. Now, and that's a very important idea, because we're talking about in those x-bar distributions, if x-bar is going to approximate a parameter, the parameter mean of population, you see, if the x-bar that we choose is going to approximate mu, then we would like that approximation to be as accurate as possible. And if it's truly a random variable, if the sample is random and the x-bar is a random variable, then gee whiz, any of these could be used to approximate mu. But if we're in a sample size of 3, any of those would be possible. And if we have a sample size of 4, any of these could be approximating mu. Now, which one would we want to be approximating mu if we want accuracy? We want the one with the larger sample size, because we want this dispersion of values to be as small as possible, because we want the error involved in our estimation to be as small as possible. That is, distance from the true mean to be as small as possible. Okay, it's a very important idea. Well, this, as I mentioned before, now, this is an unrealistic situation. This is just to illustrate a point. But the point that we're making, I think, is very clear, that we need to have larger and larger sample sizes give rise to more and more accuracy in using a sample statistic to estimate a population parameter. Now, generalizing a little bit, given a normal distribution of a random variable x, with a mean mu and standard deviation sigma, any x-bar distribution will be normal. All right, that's kind of important, that any distribution of sample means will be a normal distribution. Now that's kind of important because it allows us, in this normal idea, to use probability values that we associate with the normal curve. All right, so that allows us to use that probability association. And we know that the mean of the x-bar distribution is equal to the mean of the population. We also know, now this is new, that the standard deviation of the x-bar distribution is equal to the standard deviation of the population divided by the square root of n being the sample size. All right, so as n gets larger and larger and larger, this value becomes smaller and smaller and smaller as we predicted earlier. But now we have a relationship between our standard deviation of the population and standard deviation of a sample. All right, there's one other notion that we want to bring into play here and talk about mathematically. From a manipulative standpoint, if we're going to make some calculations, we need to bring z into the picture. We need to be able to make some z-score calculations. And we can do that here like this. From our previous discussion about calculating a z-score for an x distribution, a distribution of the random variable x, we know that z is calculated as, let's see, average distance from the mean kind of thing. So it turned out to be x minus standard deviation over, x value minus the mean divided by the standard deviation. So this gives the number of standard deviations from the mean. All right, that's what z is all about. Now, a z involved with an x-bar distribution is calculated the same way. Some of the notation kind of changes a little bit, and it changes like this. If we're talking about an x-bar distribution, then instead of having x values that we're making this z calculation for, it's an x-bar value. It's just a mean value. And we're subtracting the mu associated with the x-bar distribution, and we're dividing by the standard deviation for the x-bar distribution. Okay, all of this just associates this with the x-bar distribution. Fine. All right, now, with the information we have over there, though, we can clean this up a little bit because, after all, the mu of the x-bar distribution is the same thing as the population mean, simply mu. And the standard deviation for the x-bar distribution is related to the standard deviation of the population divided by the square root of n, the square root of the sample size. So we can clean it up this way. There's another way we can manipulate this just a little bit further, and it turns out that the square root of n will end up in the numerator. So this is the square root of n times x-bar minus mu over the standard deviation, if we want to use it this way. Either of these is okay. So to consolidate this, to make this picture complete, we might say that the z involved in this x-bar distribution is, and I kind of favor the x-bar minus mu over standard deviation over the square root of n, at least for the time being. Consider this problem. We've seen problems like this in the past. Suppose we have a population whose mean is 10.2, standard deviation of 1.4, and we want to calculate the probability that a randomly selected x from this population falls between 8 and 12. Now, to make the calculation, we can see it visually like this. Here is our distribution, and we want the probability that an x in the distribution falls between 8 and 12, and here's our mean of 10.2. Well, we know that we're going to find a z associated with 8 and 12 for this population, and then those z values, those z-scores, are associated with areas, and the areas represent probabilities, and that's how we get at the essence of this problem. Well, to first calculate the z-score associated with the 8 and the 12, we're going to use this formula, x minus mu over standard deviation, for our z values. When x is 8, then we would have z is 8 minus 10.2 over 1.4, and that turns out to be negative 1.57. If x is 12, then we replace x with 12, same mean and standard deviation, and we get a z of 1.29. So to put that into the perspective of our illustration here, for a z then, the z-scores associated with these raw scores then would be these. Let's see, associated with 8 was the negative 1.57. And we know that at the mean, the z value would be 0. And over here at 12, we found it to be 1.29. And now we would go to the table and find areas associated with a z of 1.57 and a z of 1.29. We go to the chart, and let's find the 1.29 value first. We look in the left-hand column for 1.2 and cross-reference that with 0.09 in the top row, and we find the value to be 0.9015. Then we look at the chart for the negative values, and we find negative 1.5 in the left-hand column and then 0.07 in the top row. Cross-referencing those, we find the value to be 0.0582. Now, what do we do with those? Well, these correspond with areas. That is, the 1.29 implies an area, that there is an area to the left of 1.29, and that area is 0.9015. And in a similar way, for a z of negative 1.57, it implies an area to the left that is 0.0582. We'd like the difference in these two areas. So all we do is find that difference, just calculate the difference, and we find it to be 0.8433, and that corresponds with a probability. So this probability then is 8433, like this. All right, so now we're using this problem as a reference. I want to compare this to another problem having to do with the same population, but we're going to talk about an x-bar distribution, a distribution of sample means. Now suppose we want to calculate the probability that x-bar lies between 8 and 12 if we're talking about sample size of n equals 5. So we have all of the samples of size 5 associated with this population that come from this population, and we want to talk about an x-bar distribution, a distribution of those sample means, and we want the probability that a randomly selected x-bar value will fall between 8 and 12. It's kind of similar to the earlier problem, but we're talking about sample means here in this distribution and not just randomly selected x values. And the point I'm trying to make here is, and to illustrate vividly, is the idea that the standard deviation for the x-bar distribution is a lot tighter than the standard deviation for the other distribution, the distribution of the population. Okay. To make the calculation, we start kind of in the same way. Here is the x-bar distribution. X-bar values then of 8 and 12 is what we're talking about here. We know that the mean in our x-bar distribution is the same as the mean of the population, which is 10.2. Okay, now for the z's associated with these values, the z's associated with this x-bar distribution, or in this x-bar distribution, would be x-bar minus mu over the standard deviation of the x-bar distribution, which is standard deviation of the population divided by the square root of n. All right, now let's just pop in these values. For an x-bar of 8, we would have 8 minus 10.2 over, let's see, 1.4 for the standard deviation of the population divided by the square root of 5. All right, and that gives us, punching the calculator, that gives us negative 3.51. Wow! This means, and this should jump out at us as a significant number because we're talking about 3.5, you see, 3.5 standard deviations below the mean. You see, that's a long way. That captures a great deal of the area under the curve on that side of our distribution. And so that should be a rather significant notion to us right here. So negative 3.51, let me pop that in. So here are the z values associated with these. So we have negative 3.51. And then, of course, the z of 0 here at the mean. Now, for 12, it's a similar idea. For an x bar of 12, we would have 12 minus 10.2, and then our denominator as we had before, and the z is 2.87. And that's numbers of standard deviations from the mean, so 2.87. And now we want the areas associated with these z-scores. In the table, we find that a z-score of 2.87 corresponds with an area of 0.9979. Then we look for an area corresponding with negative 3.51, and we find that it's not even there. we have areas that go to negative 3.49, and the last entry there, you notice, is 0.0002. And let's use that value for the value of negative 3.51. I think it's fairly accurate. So 0.0002 for the area to the left of negative 3.51. Now we want the difference, and we find that difference to be 0.9977, and we know that that corresponds with a probability. So the probability that an x bar value will lie between 8 and 12 is 9977. That's over 99% probability that our x bar is going to fall within this range. So the idea is the comparison, I hope, is very vivid here, that with our population distribution, when we go from a population distribution to an x bar distribution, the spread of values in the x bar distribution is much narrower than the general spread of values that are in the population distribution. Well, let's look at the situation comparing x bar distributions, sample mean distributions, and population distributions. We assumed earlier that if we have a population distribution that is normal, then the sample mean distribution, the distributions of sample means, will be normal as well. We also know that if the sample size increases, that the standard deviation of those x bar distributions becomes smaller. So here's an illustration of how that works. We begin with a normally distributed population, and here we have sample size 2. Notice it's a normal distribution as well. And here's a sample size of 10, and notice how the curve here for this x bar distribution is illustrating that the standard deviation here is getting tighter than it was here, and this is tighter than that was up here. And for an n of 30, it would look something like this. Well, notice normal, 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 all coming from a normal population distribution. Well, here's what happens if the population distribution is not normal. Suppose it's highly skewed, like this population distribution. Then what happens with the distribution of sample means? Well, if the sample size is 2, then the distribution of sample means might look like this. You see, it's also skewed. When we increase the sample size to 10, notice it's beginning to take a more normal shape. And by the time the sample size gets up to 30, it turns out that the distribution of the x bar distribution turns out to be relatively normal, or normal. Now, that should tell us something about just the general idea here in this relationship between our population distribution and our distribution of sample means. That if that sample size is large enough, then the distribution of sample means is going to be normal no matter the distribution of the population from which these samples are taken. And that brings us to, that's the essence of the central limit theorem. And the central limit theorem kickstarts a great deal of, and the most important work that we have, which is before us. Here's what kickstarts all of that possibility. The central limit theorem, given any distribution, no matter how skewed, of the random variable x, as the sample size increases, the x bar distribution approaches a normal distribution. And this normal distribution is accomplished, this normal distribution of the x bar values is accomplished when n is greater than or equal to 30. So an n greater than or equal to 30 is large enough to accomplish this idea.